Okay, so conditional probability and independence, they kind of go together, because this slide should have been right after conditional probability. That would have probably made more sense for you guys, but it is what it is. So when knowledge that one event has happened does not change the likelihood that another event will happen, we say that the two events are independent. So, for example, I wanted to go to Raley's and Walmart. Well, I said something like, okay, well, in the previous one, the condition was, if I go to Raley's, then if I don't go to Raley's, then there might be a 90% chance that I'm going to go to Walmart. But if I go to Raley's, then my Walmart probability will probably go down because I probably won't need to go shopping anymore. But if one event has happened does not change the likelihood another event has happened, we say that they're independent. So whether or not I go to Raley's has nothing to do with whether or not I go to Walmart. Okay, the probability is still the same. I'm going to go to Walmart as if I were to go to Raley's. Then we can say Walmart and Raley's are independent of each other. And the way that we do that is we use the given condition to prove it. So I'm going to use the probability of that we did for the liberal arts, physical sciences, and health and human services one to actually show you this. So, give me just a second here. Let's see, what do I want to do? I have some space up here, so I think I can do it on this side. No, up here would probably be better. Okay, so let's say I wanted to show, okay, if two things were independent. So the question is, and I'll do it on this one. Okay, is engineering independent of getting a grade level of B? Okay, we'll do that one. So the question is, is being in EP, what is this? Engineering and physical sciences independent of getting a B? Okay, that would be a typical question. Okay, so then we work it out. So is the probability of event A, EPS, given B equal to, given getting a B, I'm hoping you understand the part, equal to the probability of EPS? That's the question. And that's how you interpret this one over here. A given B, is it equal to A, or B given A equal to B? One of the two. If you can show me that they're equal, then they are independent of each other, which means the probability of being an EPS has nothing to do with the probability of, well, I shouldn't say it has nothing to do, which basically means the probability of EPS, knowing that probability doesn't actually change the probability of getting a B in whatever class you're in. So let's look at this one. So EPS given B. So you know everyone in B is 2,952. So out of this group, this is your stipulation, this is your condition now. Out of this group, you have 432 out of this entire group that have engineering and physical science degrees. So it'd be 432 out of 2,952. Is that equal to just being in engineering and physical sciences? Well, that probability is, this is 1,600 out of 10,000. So 1,600 out of 10,000. Okay, so take a look at those. Right now, it's kind of difficult to see whether or not they're going to reduce to the same thing. I mean, you can probably work some things around, but the probabilities for each one is what I'm really going to be interested in it. So 432 out of 2,952. 952. Oopsie, that's totally wrong. 432 divided by 2,952, right? Okay, so that gives me 0.146. Is that equal to, didn't we do 1600 or 10,000 already? 0.16. So, are they equal? No, they are not. So that means, and this is where you have to say it correctly in context. If they're not equal, that means they're not independent. Okay? And for right now, we're just going to leave it at that. Okay? They're not independent. All right. So, if they're not independent, then there's really not much you can do about this one. We're going to talk about other stuff later, what happens when they're not independent, and what you say when they're not independent. But right now, they're not. So, if they were, that means the probability of being EPS, the probability of this one, will not affect the probability in being in B. But it does actually affect it because they're not equal to each other. Okay. All right. And then the last part, when they're independent, you can put them equal to each other, which makes it very convenient. But if they're, and then the multiplication rule for independent events is if you know the probability of A and B are independent of each other, if they are independent, then you can do something very simple and just multiply. The probability A and B would just be equal to probability of A multiplied by the probability of B, which is what we did here, right here, when we did the tree diagram, and right here too. If I know there's a half chance that I'm going to roll a heads or a tails in the next one, I still have a half and half chance of getting a heads or a tails. So knowing that I got a heads on the first one didn't change the probability that I'm going to get a heads on the second one. It was still a half. It didn't change anything. So that's why I'm allowed to do 1/2 times 1/2 to get 1/4, because these heads and heads are independent events. But, for example, on the tree diagram with this one, I'm pretty sure this is not an independent event. Yeah, this one. The probability for this one is not independent, and you'll see that right away. If you get 0.27 for 18 to 29-year-olds, you have a much higher chance, a 70% chance of being on the site, than if you were to get a 0.45% and get 0.51. So these events are not independent of each other, because one probability actually does affect the other. Knowing this probability does affect the actual probability of being on the internet site, whereas opposed to, heads and heads, getting a 1/2 on the second one is independent of getting 1/2 on the first one. You still have heads and heads. All right. And I think, where's the rest of the paper? Okay, here we go. All right, so if that's the case, then what you do for the multiplication rule for independent events is you basically just multiply them, which makes it very, very easy to calculate probabilities. So the following Space Shuttle Challenger disaster was determined that the failure of O-ring joints in the shuttle's boosters was to blame. Apparently, they have 6 of these guys. Assuming the O-rings succeed or fail independently, what is the probability all 6 would function properly? So, if you know they're independent of each other, you can take each individual probability and multiply. So the probability would look like this. Actually, it wouldn't look like that. The probability of all of them would just look like 0.977 multiplied by 0.977 multiplied by 0.977. You get the picture. It's pretty tedious. Eventually, you have 1, 2, 3, 4, 5, 6 of them in a row. So that's technically 0.977 to the 6th power, which basically gives us a probability of, to the 6th, of 0.8696. Well, it's pretty much almost 0.87. Okay, so the probability that all 6 would function properly at the same time is around 87%. All right, there you go. If you know they're independent, you just multiply the probabilities together. You're assuming would function properly. You can do the inverse of this and say, well, what's the percent that they would function, well, that they wouldn't function properly? You would just do the complement of that, right? Presumably. Well, let's see if it actually happens. What's 1 minus 0.977? If, let's say, they failed, right, you would just do 0.023 6 times, right? So 0.023 to the 6th, and that would give you some really ridiculously small number. I get 1.48 times 10 to the negative 10, something like that. It's like a ridiculously small number that would fail technically. So you never know. Which is not 1 minus that amount, by the way. You can't just take the complement of that thing. That's not exactly how it works. There's 6 of them in there. Okay. I think that was it. There's 12 slides. Any more? Nope, that's it. Okay. So that's the multiplication rule for independent events. And you should be good to go. Sorry, there's so many videos. I didn't realize there was going to be that long of a section, but it is what it is. See you later.